Section 2.1, Quadratic Functions. So a little bit of review from what you've done previously. Let's go ahead and jump right in. So we want to rewrite this in standard form. As you know, our textbook identifies vertex form as standard form, and the form that you see here is general form. So we're basically just trying to put it in vertex form. So following along with the previous example shown in the notes, I'm just going to follow the exact same steps. So first thing I'm going to do is I'm going to factor the 2 off of the 2x squared and the 3x. So let me put some parentheses here. First thing I'm really going to do is I'm going to group the x squared term and the x term together. And I'm going to factor out the leading coefficient. So let's take a 2 out of there. When I divide by 2, my 3 turns into a 3 halves now. And then just bring down your plus 5 with you. Now, what you could do at this point when you decide to complete the squares, you can add the value to the other side and then just subtract it back over, or you can keep it all on the same side. The way that the notes have it is we keep it all on the same side. It doesn't really matter, you get the exact same answer. So now, to complete the square here, I am going to take the 3 halves and I'm going to divide it by 2, and then I'm going to square it. So 3 halves divided by 2 is going to be 3/4. Squared is going to give me 9/16. So that's the number that's going to be added to complete the square inside. Close parentheses, bring down the 5. Now, whatever I put in, I'm going to take out at this point as well. So, what I put in was this 2 times the 9/16. So, it was a positive. I'm now going to subtract it. So, again, you want to make sure that you just keep it balanced. So, minus 2 times the 9/16. Again, you could have added that to the other side and then just moved it back. That's fine. Okay, so let's go ahead and factor this now. So I'm going to match the 3 halves sign, and then I'm just going to go back up here to what I did just a second ago and look inside the parentheses here where the 3/4 is. So after you cut it in half, but before you square it, that's what goes in the parentheses when you're factoring. Bring down my 5. I'm going to go ahead and distribute my -2. The 2 and the 16 are going to cancel. So I get a 9/8. And then bring my f of x with me. And then the last thing I need to do is just combine the like terms at the end. And if I have a positive 5 and a negative 9/8, I'm just going to get a common denominator with 8, so it's going to be 48 minus 9/8. It's going to be positive 31/8. And that's it. There is my standard form now of the original function. I'm going to do the same again on my next example. Same process, the exact same thing. So bring down my f of x. Well, let's go ahead and group those 2 together first. And then take out the leading coefficient. And then just bring down your 1. Oh, I don't want to do that. Oh, yeah, I do. Okay. Then I need to figure out what's going to complete the square. So I'm going to take the value in the middle, this -7/3 here. So I go from here to here. I'm going to do -7/3 divided by 2. Always cut it in half and then square it. So -7/3 divided by 2 is going to be -7/6. And then if I square that, that's going to give me 49/36. And then just bring down the plus 1. Remember, you want to subtract what you added in. So I added in a 3 times that, so I'm going to subtract 3 times that. Again, like I said on the previous slide, if you want to move that to the other side and then just move it back, that's perfectly fine too. You get the exact same answer. You just want to make sure that at the end you have f of x equals. So 3x, match the sign on the 7/3, and then go back and take a look at after you cut it in half, but before you squared it. That's what goes in the factored form. So, and you can even just take the sign from there as well. Squared, let's bring down what we got, plus 1, and then I'm going to go ahead and distribute that, and the 36 and the 3 are going to simplify down to 12. And then the last thing is just to combine like terms. So if I get a denominator of 12, it's going to be 12 twelfths minus 49 twelfths, so it's going to be negative 37 twelfths. And I'm done. Okay, last example for these notes is the application problem. So I just went ahead and wrote out the questions, exact question that you have in your written notes already. So we have a rectangular region with semicircle on each end. The perimeter of the room is to be 200 meters long, 2 meter single lane running track. All right, so 200 meters all the way around the whole thing. We need to draw a diagram. All right, so it says there's a rectangle involved here, so I'm going to go rectangle. All right, so I'm going to have some sort of a rectangle here. So let's go ahead and draw that. Then, on the end of those rectangles, here's where it's going to get interesting because I have to draw a half circle. So semicircle on each end. All right. That doesn't look too bad. And then it says that, oh, on part A, it says to draw a diagram. So there's my picture. Let x and y represent the length and the width respectively. So since the x comes first and then it says length first, that means that x is the length here. And then it says y second and the width second. So that means that this distance is y. All right, I've got my picture. Let's take a look at the next part of the question. Okay, so now we've got part B written down. It's the exact same part B that you have in your notes. So we need to determine the radius of the semicircular ends of the track. Let's do that first. So I think what I'm going to do is I'm just going to take a little picture of the semicircular end of the track and just bring the information that I know. So there's y. And they want me to find the radius. All right, well, if this is a semicircle, it means it's half of a circle. So this y distance actually represents the diameter. And the diameter goes all the way through the center of a circle and has endpoints on the circle itself. So if y is the diameter, then half of y is going to be the radius. So it's the relationship between a radius and diameter is you cut the diameter in half. All right, so there's the radius. Determine the distance in terms of y around the inside edge of the two semicircular parts of the track. All right, so I think I'm just going to pull the two semicircle parts together because that's really what we're looking at here. So there's one end. Here's the other end. Ooh. So now what I'm looking for is I want to try to piece these together because I want to go all the way around it. So let's turn this into just a full circle. Okay, so I went ahead and added my two pieces together and I got myself a pretty decent looking circle where I know that the radius of this is going to be that half y. What they're asking me to do is they're asking me to find the circumference of this thing. So I want to go all the way around both halves, which is really just around an entire circle. So going back to geometry, ooh, I still have my circle. let's get rid of that. I know that the circumference is actually just going to be 2 pi r. All right. So I've got 2 pi. Now I know my radius. That's what I figured out just a second ago. That's half y, which means the circumference of both of the pieces together, 2's are going to cancel, is just going to be pi y. So the distance around both of the semicircles together gives us an entire circle, which is going to be pi y, the circumference of the whole thing. Okay, part C, now we've got the question for that. I want to use the results from part B to write an equation in terms of x and y for the distance traveled in one lap around the track. All right, so I'm going to go back up to my picture here. I know that to be able to travel in one entire lap, I have to go all the way around this thing. So in blue, let's say if I start down here in the bottom left, I want to go all the way across that x, then I'm going to go around the semicircle, then I'm going to go the length again, which is going to be x, and then finish with the other part of the semicircle. That's going to give me the entire circumference, the entire travel around the path. So what I'm going to have, I'm still keeping with the blue, I'm going to have the x distance plus the two semicircles together. So when I go around it in the beginning and then when I come back at the end, that's going to give me one full circumference. So I'm just going to go ahead and put in the circumference from the previous part, which is going to give me pi y plus, then I have that x across the top of the picture as well. So that's going to represent going all the way around. But back in the given information, it says that the perimeter of the room is to be 200 meter single lane running track. So this better be equal to 200. Then if I combine like terms, I'm going to get 2x plus pi y is equal to 200. So that's the first thing that it asked me to do, is write an equation in terms of x and y. All right, done. Now I need to solve for y. So I'm going to go ahead and bring my equation over here. And I know to be able to solve for y, I'm going to have to subtract the 2x and end up dividing by pi, or pi is just a number here. So there's my equation and my answer to part C. I'm going to end up flipping to the next slide and getting our question ready for that one as well. Okay, so on to part D. You got the same question that you had in your notes, and I figured I would just bring the picture with me that we drew earlier, and then it says to use your answer from part C, and instead of having to flip back and forth on the slides, I figured I'd just write down the equation here. So they want me to write the area of the rectangular region as a function. Okay, so just the rectangle. So the area of the rectangle, well, the area of a rectangle is just base times height. In this case, it's x and y. And the problem is that's not the answer. I want to write it as a function of x, which means that the x is the only variable that the area is equal to. So what we need to do is we need to replace y with something. Well, that's where the answer from C comes in. If you take a look at this, this is already equal to y. So we're just going to plug it in there so we can get rid of the y's and have just x's involved. So take out the y and put in what we found out it's equivalent to. That is the area of the rectangle as a function of x. So that means that it's going to be area equals, where on the other side, the only variable that's involved here is x. So this is area as a function of x. If you keep the x and the y involved together, it doesn't answer the question. Okay, now on to part E. We want to use our calculator to be able to graph the function that we got from part D, and then we're going to use the graph, or I think I'm going to use a different part of the calculator to approximate the dimensions that will produce a rectangle of maximum area. Okay, so the keystrokes that I'm going to be doing here, I am going to go to my y equals button. That's the first thing I'm going to do. I'm going to clear out anything that's already there, and I'm going to type in for y1, I'm going to type in the equation that we got above. So I'll do x, and make sure that you use parentheses here as well when you type it in. After I have that typed into my equation, I don't want to sit here and guess and see what my window should look like. So there's a couple ways that you can do this. You can go to Zoom, and then from there you can go to Zoom Fit. That's one way to do it. It kind of depends on the question for me. Sometimes I'll do that and go, I don't really like how that looks. So the other thing that I will do, and I'm a big fan of this feature, is I go to the table. So I go to my table just to see kind of what's happening with this thing. And then just take a look. So you want to see what's going on with your x and your y values. So I did my Zoom Fit, and the graph really doesn't look all that impressive to me. When I take a look at the equation, I know that this thing is supposed to be a parabola. But when I do Zoom Fit, well, for me, and it should do the same for you, it kind of gives me this curling effect. But then it stops. It doesn't show me what the max value is going to be, which is why I go to the table. When I'm looking at the table, I just start, well, I know that these represent dimensions of a rectangle, so I'm not even going to look at the negative x values because it doesn't make any sense. So I'm going to start at 0, and I'm just going to scroll through my table. I notice as I'm scrolling through my table that I'm in the 10s, the 20s, the 30s, the 40s, and my x's, and my y's are still going. They're getting bigger and bigger and bigger and bigger. So I'm like, okay, well, I haven't reached the maximum yet. This thing is going to have to turn around at some point. Then I got to 51, actually 50. At 50, I got 1,591.5. But then at 51, it came down. It's at 1590.9. So I'm thinking that the maximum might be somewhere around 50. So if I had to approximate from a table, so from my table, I would say that the x maximum is probably going to be about 50. You can change the increments on your table as well to see if maybe you can get a better idea of it, but I'm pretty happy with 50. It gives the largest y value. Now, the y value that we typed in, remember we typed this in as y1 equals, well, that was our area function. So we need to find the y that goes with this x. Remember, we wanted to find the dimensions of this thing to give us the maximum area. So now I need to find y. To do that, I'm just going to go back up to my blue equation that actually related x and y. So bring that down here. Plug in my 50. So it's going to give me negative 100 plus 200 over pi. So I'm going to say that my y value is probably 100 over pi, which when it comes to dimensions of something, doesn't really necessarily make any sense. So in my calculator, I would probably do 100 divided by pi. So I would say that this y value is going to be approximately 31.8309. So I would say that the length that gives me the maximum is going to be 50, and the width that gives me the maximum, we're pretty close to it, is going to be that 31 and some change. Okay, so a little bit more practice with your calculator, and basically taking two different pieces of information, one where the perimeter is kind of given to you, you have to come up with the equation for it, and then the area itself. So hopefully this should do it for this section.